And I'd just like to remind everyone that next week we'll meet in room 454 of Newberger Hall, and then the week after that we'll be back here in room 204. So today I'm very pleased to introduce Professor Yinhai Wang from the University of Washington, Department of Civil and Environmental Engineering, and he's here today to talk about monitoring freeway systems in real time using existing single-loop detectors. It's all yours.
Thanks, Rob, for a nice introduction. It's my great pleasure to get this chance to talk to you the research at the University of Washington in the ATIS group. My topic is how to use the existing single-loop detectors to monitor the freeway, estimate freeway speed, and also get classified vehicle data. Can you hear me well? Okay. Here is a brief introduction of myself. I got a bunch of degrees. You don't need that many degrees because you need one is enough. And my field covers traditional transportation field, civil engineering. My undergraduate degree was about structural engineering, actually. And I have a degree in construction and also computer science. Here it shows my website and email address. If you're interested to find more, you can visit my website. There are also cartoons there, okay? Before I start, let me ask you a question. The question is, what is the most visited website in Seattle? What? Traffic conditions? Exactly. Yeah, I think I gave the same question to many different university students. Only the student here got the correct answer. So you're all very smart. It's not Google or Yahoo. It is not MSN or Seattle Times. It is the Puget Sound traffic condition website. We also call that traffic flow map. You may wonder why, because when I first came here, I thought maybe Seattle Times should be the most visited website because that contains lots of local information, right? But actually it isn't. And I learned a lesson, and now I remember traffic information is very important. The lesson I learned was about picking up the summer school for my daughter. I have a daughter, now it's 9 years old. 3 years ago, when she was 6, I tried to find a good summer school for her, and I searched around. I found here, shows by the star, has a good summer school, and here is the University of Washington where I work. So I thought, okay, it's only 5 miles away. It takes maybe less than 10 minutes. So I decided to put my daughter there, and the whole summer I have to commute, cross this 520 bridge 4 times a day. So that one, you can imagine, I suffered a lot from that. Why? Because if the traffic conditions look like this, it's very clear that it takes less than 10 minutes to get there. But that's not always the case. If the case looks like this, you never know how long it's going to take. My experience was from 10 minutes to 2 hours. Sometimes you spend an hour just want to get onto the bridge, and then another hour on the bridge, which is only 3 miles long. So after looking at this example, I believe you agree that the traffic information is important. And also, I look at the traffic information website every day before my departure. I want to make sure I don't waste time waiting there. Meanwhile, I should get there on time. Why is traffic getting so bad? Let's look at this picture. Here, the green line shows the road capacity added from 1980 to the year 2000. The other line, the red line, shows the total vehicle miles traveled. So in the 20 years, the total vehicle miles traveled up 80%. And the road, 2% only. So, and this gap is getting bigger. There's no sign showing that the gap is start to get smaller. So that means we have to deal with this kind of traffic condition. Okay, let's look at the condition in Seattle. This is the ranking in the year 2000, and Seattle was ranked the 5th. And a year ago, I think that in year 1999, Seattle was ranked, I think, the 2nd. So this year, the new ranking, that's for the year 2001, Seattle is the 9th. But we see a new star, which is also the job security for you guys. You got number 8 in the country. So the traffic congestion in the West Coast is becoming more and more serious. So as traffic professionals, we have to deal with that. What are the countermeasures? Because we all traffic engineering professionals, we are supposed to solve these problems, right? So what's your countermeasure? Give me some idea? Yeah. Other roads? And what's your proposal?
I'm sorry, everyone should ride bicycles.
Oh, that's a good idea also. Yeah, I think new construction is definitely the traditional solution, and people tend to think it that way. And another solution, as you mentioned, don't drive your car. You can take bus, or you can ride your bike. So this involves the traffic demand control, and also it involves if you can improve the transit service. So many people would like to take the transit. There's one more solution, that is to increase the capacity of the existing infrastructure by employing ITS technologies. Let's look at how these countermeasures may work. First, let's look at new construction. As you know, most serious congestions are normally in cities where everything is expensive. Also, we need to address a bunch of questions like where it's constructed, when. People will say, oh, don't construct new roads through my backyard. Don't go through this neighborhood. And will the new roads solve the current problem? Maybe. Will the new roads also create another problem? Not sure. Okay, here is a slide showing the role of transit. Definitely, transit will play a much bigger role. For example, we have developed this kind of application that shows the bus locations in real time so that you can find the convenient time to go to the bus stop and take the bus. This will definitely help people to switch from driving themselves to take the transit. But the transit also has a capacity. This picture was taken when I was in Japan. You see, it's very crowded, and when I was in Japan, I have to commute through the railway, and it was about an hour and 20 minutes one way. So every day I take maybe 3 hours on this kind of crowded train. So if the transit also close to its capacity, we cannot really do anything on that. So the third solution will be to employ ITS. So this has been enforced in many new initiatives, also in the ICT Act. So the ITS shoots for reducing travel time, easing delay and congestion, improving safety, and also reduce pollutant emissions. You may want to know whether this solution will work. Let's look at the picture here. This is the picture 100 years ago showing a congested intersection in London. And the first solution to control intersection looked like this. There's no signal, but you got a sign saying go toward this direction, right? And this really works. So we didn't have serious congestion for several decades, right? Now we start to get the problem again. Historically, new technologies have helped to reduce the traffic congestion. Now, I believe the new technologies will also help. This picture shows a snapshot of the traveler information broadcasted by University of Washington's cable TV. Basically, you see there are two kinds of information. One is the larger scale traffic speed information. This is the freeway network in Seattle. And also, for a particular point, you can see the video image captured by the surveillance video camera. You may want to know how these information are produced. Different colors showing different speed, right? Like red shows speed from 0 to 19, and green shows speed higher than 50. Here is the architecture of the so-called Advanced Traveler Information System. Basically, there are three major components of the system. The first component is the sensor or the detector. The detectors measures the traffic and then send the information to the roadway cabinet or the stations. And then in the controller, the data is aggregated into maybe 20-second or 30-second intervals. In the case of Washington, we use 20-second period. In California, they use 30-second period. I don't know how long it's used in Oregon State. But anyway, this is the first component. The second component will be the data management and the storage. You'll see the data server and the data archive storage, and also data warehouse where you can access information. The third component will be the data processing and modeling, because the direct measurements from the detectors may not make sense, something that traveler is not interested in. So we have to convert that kind of raw data through models and produce some information that the travelers would like to see. And once those informations are produced, we put the traveler information to the application server, and the users can access that through TV or use the internet. So far, I have covered the background for today's talk, and I've focused on the loop detection technology today. We will explain the problems with the current speed estimation algorithm, and the problem is serious, so we need to propose a new algorithm to address those problems. The new algorithm is actually based on pattern recognition and also nearest neighbor decision rule. So we can not only give speed estimation, but also produce very good classified vehicle data. So those data has been verified using the true data on southbound I-5. We selected 4 stations to verify the data. And for a particular station, we collected 4 days data continuously to see whether the algorithm works well for different locations and at different days. According to Traffic Detector Handbook, the loop detector is defined as the device that senses a change in inductance of its inductive loop sensor caused by the passage or presence of a vehicle near the sensor. The loop detectors are typically in the following shapes: square, round, or other shapes. And I believe most of you saw this before, no matter you noticed that or you didn't notice it. Actually, it's very common in the West Coast. How does a loop detector work? So suppose a vehicle drives close to the edge of the loop detector, and then the detector sensed the presence of the vehicle, and the inductance dropped from high level to low level. And when the vehicle drives away from the sensor, it goes back to the normal level. So this is how a single loop detector works. And you see this kind of change of the inductance, you know there's something metal on top of the loop for this long, from T on to T off. Suppose this is the measurement in the time interval, suppose it's 20-second interval. If we see a curve like this, do we know how many vehicles presented? Three, yes. We have 3 vehicles because you see 3 jobs, right? So that means the single loop detector can measure number of vehicles per interval. And also, do we know how long the vehicle stayed on top of the loop? Because you see that the length of the red line here shows that, right? So we also know, actually we say we know the scan count. And from the scan count, we can convert that into occupancy, which is a very important measure for traffic performance. There's another kind of loop detector, which is commonly called speed trap, or dual loop, or double loop. That means you put 2 single loop detectors together, separated several meters apart. And you know the distance already. You also know the loop length. So you know this kind of configuration can measure vehicle speed, right? Because when vehicle arrives to the first loop, you know the arrival time. And you also know when the same vehicle arrives to the second loop. You know the time for the vehicle to traverse this distance. You can easily calculate the speed. And if you know the speed, you know how long the vehicle was on top of the loop. You can also calculate the vehicle length. And based on this information, you can classify vehicles into different categories. In the Washington state system, vehicles are classified into 4 categories based on vehicle length. So now let's summarize what the loop detector can do. A single loop detector can measure occupancy and volume, right? And the dual loop detector can measure traffic speed and classify the vehicle volume. We call it bin volume. So which of the 4 measures is the most valuable for travelers? Of course, speed, right? It doesn't make sense for travelers to know, okay, what's the occupancy? And they don't care like the bin volume. So speed is the most important variable for travelers. So speed is important. But is speed available from single loop? No. Speed is important, but another very important information we can get from dual loop detectors is how many long vehicles, how many short vehicles, or in other words, how many vehicles in bin 1, how many vehicles in bin 2, bin 3, and bin 4. So from the planning and operation concerns, we want to know long vehicles because they are so different from the passenger cars. They are too big. They have a heavy weight, and also very large turning radius, and also acceleration, deceleration are very different from passenger cars. We don't want a truck to stop and start very often at the intersection. Otherwise, we have to spend more money on the pavement. Also, the pavement requirement. All these things make us eagerly know how many trucks in the flow. There are also safety concerns because long vehicles or long trucks account for only 3% of the registered vehicle, but it should be responsible for 9% of the fatal accidents. So the truck data or the long vehicle data is also very important for us. However, there are not many dual loop detectors deployed in the country. So if you want to put another loop at each single loop station and make that single loop a dual loop, you can do that, but it's expensive. You need to spend from $3,000 to close to $6,000 for each loop. And this is still the data I got 3 years ago, so now I suppose it should be more expensive. It's not only because of the loop device, but mainly because the indirect costs, like you have to close a lane to do the upgrading, and that one costs lots of delays. And if you convert that into money, that's a lot. So making the existing single loop detectors capable of providing better speed and the vehicle data is of practical significance. And today, I'm going to present you an algorithm we developed at the University of Washington for this purpose. Before I introduce the algorithm, let's look at the data format. This shows the loop detection system at Washington State. We have loops deployed on the major freeway system, and these loops transfer the real-time measurement to the station cabinet. And in this station cabinet, the data are aggregated into 20-second interval and then transferred to the TSMC, which stands for Traffic System Management Center. And there, the data are archived to some media. Meanwhile, it's pushed to the internet application server, so everyone can access the server and download the data in 20-second intervals. So the data will look like this. It contains a time mark and also how many vehicles in that 20-second interval. And the last item here shows on the screen is the occupancy. Actually, the Washington system produced the scan count, but normally in other systems in the country, it shows occupancy, so I just use occupancy instead here. And then lots of research has been done to use the single loop measurements to estimate traffic speed. This is a traditional algorithm that is widely used. Washington State DOT also used this algorithm, and I know Illinois DOT has also used this. So I'm not sure which algorithm is using here, but this is a widely accepted algorithm. In this algorithm, the speed estimation parameter G is regarded as a constant. And if it's a constant, the vehicles must have a uniform length. That's the assumption. Otherwise, you cannot conclude that G is a constant. So this algorithm has problems, even it's simple. Here, see, N is the traffic volume that's available from single loop, right? Occupancy is also available. This big T is the interval length, which is 20 seconds for Washington State. So there's a problem with this algorithm. What's the problem? That's because the uniform vehicle length assumption is very difficult to meet. Let me show you an example here. Suppose this is a condition on a freeway and the speed limit is 60 miles per hour. If you are a driver and driving under this condition, which speed will go? 70? Yeah, I believe you are honest. Yeah, I will drive also at least 70, but I won't tell police about this. But let's see what's the system estimated speed. Here in the blue circle is exactly the location that's shown in this video image. And the color is now yellow, right? What's the yellow show? Shows speed between 35 to 49. Is it so slow? Of course not. So the speed is underestimated. Why is it underestimated? From here, you can see there are lots of big vehicles or trucks here. Probably that's something related to them. But let me show you another extreme case to show the problem with the algorithm. Here, suppose in 2 consecutive 20-second intervals, we have 1 vehicle in each interval. At interval t, we have only 1 short car. At the next interval, we have just 1 long truck. Suppose these 2 vehicles are all traveling at 60 miles per hour. And the effective vehicle length for the long truck is 60 feet. Here, effective vehicle length is the addition of the vehicle length plus the length of the loop. So it's called the effective vehicle length. That's actually the length a loop detector can see. Let's calculate how fast the speed is. For the short vehicle, we see the calculated speed is 66 miles per hour. It's higher than the actual speed, but that's okay. That's not too much difference. But for the truck, the speed is only 22. That's too low. It's only 1/3 of the true speed, right? So what's the problem? Is that 3 times difference? No. We see that they all drive at the same speed, 60 miles per hour. So the short answer on why they give different speed estimation is that the g value we choose was a constant, but actually for these 2 scenarios, the g should not be the same. And then what is the g related? Here, from this formula, we know the occupancy is actually equal to the sum of all the single vehicles on time divided by the interval length. And then from this equation, we can get the g actually is the reciprocal of the mean effective vehicle length. So that means if we know the mean effective vehicle length, we can calculate the g. If we can calculate the g, and we use this correct g to calculate speed, what happens? Let's see for that same example, but this time we use their vehicle length to calculate the g, and use this g to calculate the speed. Oh, it's 60 miles per hour. Now it's correct. Again, the truck is also correct. So from this example, you know the key point is how to get the correct g, right? But if you want to get the correct g value, you must know vehicle length. Is vehicle length measured by single loop detector? No, we don't have that. So we have to find a way that to estimate vehicle length, or find another way that gets rid of the effect of the long vehicles, so that we can still use the traditional speed estimation algorithm, but it will give us the correct speed. So before we do that, let's look at the vehicle length distribution. This distribution is observed by a dual loop detector on southbound I-5. We see there are 2 peaks in this histogram. The first one is very high. This represents the concentration of short vehicle length. The second peak, which is lower but broader, this represents the length concentration of long vehicles. If we separate the total vehicles according to their length, if it's longer than 40 feet, we say that's a long vehicle. Shorter than 40 feet, we say that's short vehicle. and we look at each vehicle length distribution individually, we have these two figures and also the statistics. For the short vehicle, the mean length is 0.48 meters. It's close to 18 feet. And the variance or standard deviation here is 0.87 meters. But for the long vehicle population, the mean is over 22 meters, and the variance of standard deviation here is 3.59 meters. This tells us that short vehicle length doesn't vary much. It's very close. But for long vehicles, the length difference is big, right, from this statistics. So for any interval k with nk vehicles, short vehicles detected, that means for a particular 20-second interval, there is only short vehicles, no long vehicle. In that case, we can use the observed short vehicle length from the last slide to approximate the mean vehicle length for this interval, right? Because it doesn't vary much, so the result should be close. Especially if you have more vehicles in this interval, and you got the average of that, and the error is even smaller. For example, if we have 9 vehicles detected in this interval, and we know the observed mean vehicle length is 5.48 meter, and the variance actually is only 1/3. No, not, the standard deviation is only 1/3 of the standard deviation from the observed vehicle length distribution, right? Because we have more samples, and the variance should be calculated by equation A, and we get it's only 0.29 meters, less than 1 feet. Very accurate, right? So for intervals containing only short vehicles, we can easily calculate the G. Because if there are only short vehicles in this particular interval, we can just use the observed short vehicle length to approximate the mean vehicle length for these short vehicles. It won't give us big error. But if there's long vehicles in the interval, what shall we do? Let's look at this single loop measurement again. If we can get the on-time data for each individual vehicle, and the data look like this, we have 4 vehicles here, right? And each on-time is shown at here. Do we know which vehicle is longer and which vehicle is shorter? Just based on this data. Yes? Number 4.
I would say no. Number 4 could just be a really slow vehicle that's passing over it.
Exactly. We cannot just conclude which is longer, which is shorter, based on only the on-time. We have to consider that the effective vehicle length is equal to the product of speed and on-time. But for freeways, mostly the vehicle speed are very similar, right? If we can assume that the speed are constant, and then we can just infer the relative length from the on-time. But for a single loop detector, remember we don't have the measurement for each individual vehicle. Instead, we have the aggregated measurement for 20-second interval. But follow the similar idea, we can still guess that maybe in interval 5, we have some long vehicles there because the on-time per vehicle is bigger than the other intervals. So we need to make assumptions to solve the problem. Our first assumption will be for a certain time period. The period here I use different from the interval. It's longer than interval and it contains several intervals inside. For example, the period length could be 1 minute, and then there are 3 20-second intervals inside, right? It could be 3 minutes, and then it contains 9 20-second intervals. So suppose within that time period, traffic speed is consistent because it's the freeway and the time is not that long, so this is a reasonable assumption. And we assume the second assumption is there are at least 2 intervals that contain no long vehicles in each period. Suppose you choose the period at 3 minutes. There are 9 20-second intervals. And within the 9 intervals, suppose there are 2 of them contain no long trucks. The reason we want to get this is we want to set up the ruler. With this, we can measure other intervals. Are these intervals reasonable? I think it's reasonable because you see, I checked the data for 24 hours, and the speed change larger than 15%. It's only, I think, 46 out of 288 periods, 5-minute periods here. Given the long vehicle arrival rate as 0.47 vehicles per 20-second interval, the probability of violating assumption 2, which is the at least 2 intervals doesn't contain long vehicles. The violation rate is the probability of violation is only less than 1%. So based on the 2 assumptions, I propose a 3-step algorithm. The first step is you look at all the 5-minute interval measurements simultaneously. And then based on their relative relationships of the on times, you try to separate this whole group into 2 parts. One part contains only short vehicles. The other part may contain long vehicles. So, and the second step is you can use the group 1, which contains only short vehicles, for speed calculation. Because for short vehicles, you have know that the length varies very narrowly, and then you know the mean vehicle length already, right? And that's the majority of the vehicles on freeways are short vehicles. So the third step is, after you calculate the speed, and if the speed is reasonably accurate, you are able to calculate how many long vehicles in each of the group 2 intervals. By doing so, a single loop can work somewhat like a dual loop. We don't put another loop there so we can save money. So because only talking the algorithm is kind of boring, so here I show you the picture and use this picture and to illustrate the methodology. Suppose we choose the period length is 5 minutes. That means we have 15 intervals, right? Suppose this is the 15 interval measurements for the loop detector. And actually, the data you can see is at the rightmost column. That's the data you can access. But here, suppose these vehicles presented in each interval. And then the first thing we need to do is we need to calculate the on time per vehicle, right? On time per vehicle and sort it up. So I would like to skip this mathematics because when I was a student, I hate to read these things in a short time. So, but if you have interest on this, want to discuss with me, you are welcome. After the seminar, you can come to me and talk about these things. So here, I just skip these things and illustrate the algorithm. So after you sorted the intervals, you'll see these are all 0 intervals without any vehicles. And you should cut these intervals because they are not useful at all. Just drop these things, and now you have 6 intervals contain vehicles. And what you are going to do next is based on the occupancy per vehicle, because this can easily be converted to on time per vehicle. You try to compare some critical value and then figure out which interval belongs to group 1. That is the interval only contains short vehicles. which interval should belong to group 2. That means it may contain long vehicles. So here you set up a critical value alpha based on the distribution features, and then you compare each interval with the short vehicle length. If it's larger than alpha, you assign this interval to group 2. Otherwise, you assign it to group 1. So suppose now you have finished the classification. Now you got the non-zero measurement intervals successfully separated into 2 groups. So here is group 1 with 4 intervals and the group 2 with 2 intervals. Which group in interval measurements should we use for speed calculation? Which one? Group 1. Yeah, because these are all short vehicles. We know the short vehicle length, and we know that sufficiently close to the sample vehicle length because short vehicle length doesn't vary much. So we can use group 1 to calculate the speed. So after the speed is calculated, we have another problem to solve, right? That is to figure out how many long vehicles in each of the group 2 intervals. So here I propose nearest neighbor decision rule to identify the numbers of long vehicles in each group 2 interval. So the way we do it is we need to have some pre-classified categories. How to set the pre-classified category? Here we set it up based on how many long vehicles it contains. Suppose the maximum number of long vehicles in one 20-second interval is y, then we have y plus 1 predefined categories, right? Because you have the categories corresponding to the number of long vehicles from 0 to 1 to y. So that's why you have y plus 1. If you have any questions, just feel free to stop me, okay?
Well, I mean, in that, when group 4, when category 4 have automatically been, based on your assumptions, that would have been in group 1.
Yeah, but there's a possibility that because this kind of classification is based on the on time per vehicle, and it's not exact measurement. Yeah, so I say for group 1, you are sure these are intervals without long vehicles. If you set it strict, you get a better speed measurement, right? Estimation. If you're not that strict on the critical value, and maybe some interval contains long vehicle also mixed inside that, and that will make your speed estimation inaccurate. It doesn't hurt. Finally, we found, oh, I thought you are group 2 interval, but actually you are not. It doesn't hurt because we don't lose anything.
Okay, so your group 1 interval is much stricter than your group 2.
Right. So
okay.
group 2 is the intervals may contain long vehicles. That's a very good question. Thank you. So, for example, we have 3 vehicles here, and these 3 vehicles may all long vehicles, or it may be all short vehicles. So in total, we have 4 predefined categories. And then we use mean effective vehicle length to calculate the distance between the unknown pattern to each of the predefined categories. The unknown pattern is the current interval. You don't know how many long vehicles, how many short vehicles, right? And you have pre-classified category, and you want to match which one is the closest to this unknown one. If you know this one is very similar to the second one, and then you know there's 1 short vehicle, 2 long vehicles. So the way you calculate that is through these equations, and here is how the distance is calculated. Now suppose we have done the distance calculation, we have two intervals that are in group 2, right? And suppose interval 14, we calculate the similarity to each of the 3 classified categories. We have only 2 vehicles, so there are 3 classified categories, right? And we calculate the distance. Suppose the distance is 0.42, 0.05, and 0.63. Which one is this unknown pattern most similar to? The second, right? So we say, okay, this unknown pattern is actually pattern 2. And now we got this one short vehicle, one long vehicle. Similarly, for interval 15, we can do the same calculation and pick up the one that with the smallest distance. So now we know for this 5-minute period, we have 3 long vehicles, 12 short vehicles. So now we figure out both the speed and also the long vehicle's volume. So this should be exactly what we expect from the dual loop detector, right? So to verify the algorithm, we picked up 4 loop stations on I-5 in Washington State. And these are the stations we picked up. At each station, we selected one lane for the calculation. For a particular loop station, we also collected data for 4 consecutive days. So this is the speed estimation for 4 consecutive days. So these 4 days covers both weekdays and weekends. We see that during the weekday, there is some congestion, and this algorithm matches this congestion also very well. It synchronized with the true speed that's shown by the red color, and the estimated speed is shown by the green color. So for weekdays, they work fine. For the weekend, they work even better. This graph shows, the first one shows the estimated long vehicle volume at each of the 4 study stations. Basically, the 2 curves, the green curve shows the observed long vehicle volumes by the dual loop detector. The red curve shows the estimated long vehicle volume. Basically, they synchronize well, but here, which near the morning peak hour, the error is larger, right? Here is also one station for 4 consecutive days, and we see that during the weekend, there are not as many long vehicles as during the weekday, and also the algorithm works better over the weekend. These 2 tables show the statistic results. Basically, the speed estimation is very good, so the error is small. For the long vehicles, there may be individual errors that's large, but if you add all the 5-minute estimations into 1-day data, the maximum error is smaller than 8%, which should be sufficient for planning purposes. Now let's discuss what we found from this study. So when traffic volume is high, traffic speed is less stable. Right? We had 2 assumptions to support this algorithm. Were the 2 assumptions true? No, not always true. Otherwise, it's truth, not assumption, right? So there are some problems if the traffic volume is high, traffic speed is less stable. Assumption 1, which is a constant speed assumption, may be seriously violated. And the violation of this assumption can cause the long vehicle volume to be overestimated. Because some vehicle gives longer on time, actually it's because speed is low. It's not because the vehicle itself is wrong, right? And the violation of the second assumption is also likely to happen when the traffic volume is heavy. So this can result in underestimation of both wrong vehicle volume and speed. So if this assumption is violated, that means you thought these two intervals should not contain any short vehicles, but actually they do. So it's like you are using a ruler which is not accurate to measure the rest of the interval, right? So this will make the bias estimation. So as a conclusion, the proposed algorithm can produce very good speed estimates and also reasonably good wrong vehicle volumes using only a single loop measurement. We have demonstrated the whole algorithm, right? And to some extent, a single loop detector can perform like a dual loop detector using the proposed algorithm. The proposed algorithm works well under normal traffic conditions, but will not work when the traffic is stop and go. Why? Because the assumptions are not true. If the assumptions are not true, the algorithm may not work. Question?
When you say the assumptions are not true, you're saying that in heavy traffic, like a short car might take 3 minutes to cross because they're really in traffic, and then all of a sudden something opens up, and a longer truck will take 2 minutes to cross the same thing because it kind of goes and goes.
Yeah, the idea is the same.
Okay.
But as I said, we have two assumptions. The first assumption is a constant speed, right? That thing will happen when speed is not constant. The proposed algorithm does not need complicated calibration, and is easy to apply. I have some comments for future studies. The first one is we need to do quantitative analysis on the effects of the violating the two assumptions. If the first assumption is violated, what's the error because of the violation? We need to know that. And also, guiding rules for period length selection. The data and the calculation we have done is based on 5-minute period. What about 3 minutes? What about 2 minutes? So we need to do more work to see which time period may work better. So the automatic detection for assumption violations and the appropriate corrections are necessary for real-time applications. Because you may implement the algorithm in the loop station, and then you leave the algorithm there. But if the traffic is congested, and you know it's not going to work well, but it doesn't aware of the congestion, so the data will be not good. So if it's automatically detected, the violations, and then maybe figure out a way to handling these cases, that will be more favorable. And spatial and temporal transferability needs to be further tested with site data from other freeways. Like, will the same algorithm work for Portland, for California? So we need to test that more. Based on this algorithm, Dr. Yinhai and I developed, we have made a computer application to monitor the freeway system. So here is a snapshot of the system. This system basically provides you the freeway network and use different colors to show speed levels. But be aware that here the color we use is different from the WSDOT color, Washington DOT color. So red here is not that bad, actually. Be aware of this. And if you want to look at a particular loop station, you can move your mouse there and click it, and it will pump up a window shows the details of that station. So I will demonstrate this system later. Another application we developed is we call it event data mining module, event data mining system. In this system, we use event data, not just 20-second archive data. Event data means you poll the loop detectors 60 times per second. So that means you know very detailed when the vehicle arrived, when the vehicle left. So that kind of data is very helpful for you to tune up the loop detectors or identify the loop errors. So thank you for your attention, and here is my presentation. I would like to spend some time to answer your questions, and then we will demonstrate the program. If you have questions about the program, I would be happy to answer also. Yes?
You mentioned at the beginning that one of the reasons for this was rather than it's a high expense of adding a second loop detector, the reason for even asking all these questions. So for locations such as Portland or San Francisco who have also maybe a lot of single loop detectors and don't want to invest that money, how much is this process? I mean, is these mathematical algorithms free? How much would it cost to monitor or increase or change the count processes in the programs? Is it actually cheaper?
Yeah, actually, there's no cost for this. It's already published in Journal of Transportation Engineering. You can find the paper from the journal, or you can download from my website. And to implement the system, actually, it's also very easy. You implement that and put that into the controller. It will work for you. And this work is done by the support from Washington DOT. It's a public resource already. So I think it's very cheap, but the problem is whether the DOT have the controller that is powerful enough to implement it. Like in Washington DOT, the controller was the product in 1970. So that means that controller has very limited computing power. And if you put more things there, probably it will not handle. So now this has been developed, and now it's only for offline application. Like I can give you the program, and you can try that, and it's offline, it's not online data collection. But we developed the Freeway monitoring using the 20-second data. That's in real time. So for monitoring purpose, it's perfect. But for specific data collection purpose, if you want to host the program in the controller cabinet, maybe it depends on the capacity of the controller. If you just want to run the program to provide better information, it's free, no cost. We have developed it, and you can download the program from our TransNow ATIS group website. Yes?
How accurate are double loop detectors in heavy traffic flow?
That's a good question. If the dual loop detectors work well, it should be very accurate. But there is a research undergoing in the University of Washington. They got research funding from Washington DOT and used the event data try to tune up the dual loop detectors. Because once the loops are placed into the location, and it may be accurate at the very beginning, but with the time change, the two loops sensitivity may not agree with each other. So that means the same vehicle may be viewed differently from the single loop. And the system may think, oh, this is not the same vehicle. And then it's just drop it from classification. So in the Washington State loop detection system, maybe only less than 20% of the dual loop detectors are actually working correctly. So that's why we are doing a research to fix those dual loop detectors. So if we can fix those dual loop detectors, I think they should give very accurate count based on vehicle length. But sometimes, the vehicle length is viewed by the loop detectors according to the inductance. If the vehicle is long, but actually it's not metal, it's plastic, it cannot be detected by the loop detector. Yes?
What percent of the loop detectors on the road in the Seattle area are double loop detectors, and how far apart are the loops?
That's a good question. In Seattle area, we developed lots of dual loop detectors. In the core part of downtown Seattle, like I-5 through the downtown part, and also through 405 through the downtown Bellevue, that section, we have lots of speed traps. In that area, probably close to 30 or 40% of the loop detectors. But nationwide, dual loop detectors may be only less than 10%. For example, I heard from some researcher in Minnesota, they have no dual loop detectors in the state. All the loop detectors are single. Yes?
I guess that leads to this. How far was the scope of the scale? Did you go from Tacoma? Because I know Tacoma to Seattle, that's a lot of traffic in that area. Did you go out that far, or were you just interested in the Seattle area? And what other type of detection systems are they employing in your study area?
In Washington State, the majority of the sensors are still loop detectors. It has been in place for over 20 years, I think. And in Tacoma area and the Seattle area, because the weather are so similar, I believe we use the similar detection technology. But in the West Coast, it's warm, there's no snow and ice, so loop detector is a very favorable detection type. But for Spokane, there's snow there, so this morning we just had a meeting with Washington DOT staff, and we were told in Spokane area, no loop is installed. All the new installations are video sensors. Yes?
Have you investigated using dual loop, upstream dual loop information to modify your assumptions in real time that are going in, because they can give you some data that you're assuming are constant?
All our research that's been done so far use the freeway data. We haven't used local road street data yet, because now the freeway has more serious problems.
I mean, on the freeway, you'd place a dual loop upstream of a single loop, so you're
Okay.
not always single loop, but you're getting an idea of what's coming toward you, so you can get a better estimate.
Okay, yeah, I think that's a very good idea. Actually, several researchers have been using the information from the nearby dual loop stations try to calibrate the single loop. But in this research, we just focus on single loop. We don't take any information from the adjacent dual loop detectors, because even the nearest dual loop station is at least half a mile. Within the half mile, many things can change. So we trust only the local detector for this research. Okay, if you have no more questions, maybe we can take a look to the system. So this is the system that we implemented. Actually, you see the color changes every 20 seconds, because every 20 seconds we download the real-time measurement and calculate using the model we just presented today, and shows the traveler information. You see here, southbound I-5 here is normally very congested. Northbound is okay at this moment. The 520 bridge is not yet start to be congested yet. You can see this is just the speed data. You can also see how many large vehicles here. You see some interval has 2 to 4, some interval has 5 to 7. Most of them has less than 2. So you can see immediately the long vehicle distribution on the network based on this system. You can also see the short vehicle distribution across the network. You can also try to see we can see this is a loop station. If you click it, all the loop detector code will be pumped up. You can select, like we select this MSS2 loop. And then the window will pop up, give you detailed information about the loop. So now the speed is 22, and small vehicles 5, long vehicle 0. It's congested there. So this the system that we developed for real-time freeway monitoring. We have also other applications, not yet online, but if you are interested in, maybe I can take a few minutes to show you another one.
I'm sorry. What do the numbers mean in the legend? You
Which
have
number?
like the numbers in the legend. What do they mean?
This?
Yeah.
This is number for short vehicle, small vehicle.
Oh, okay. So you have it up there. Okay.
Yeah, it should be small vehicle numbers. So this system was developed by Hudong, who helped me during the research, and also I developed the engine, he developed the user interface.
I had a quick question.
Okay.
I think before you said that the maximum percent error between the your algorithm and the dual loop was 8% for classification.
Yeah, the long vehicle volume error, daily long vehicle volume error is the maximum error is less than 8%.
I guess my question was similar to what Tashi asked before about the percent or the order of magnitude of the percent error between the cycle data and, say, the 20-second aggregation. Like, we don't have cycle data here. We have only 20 seconds.
Mm-hmm.
And a lot of times people ask, well, what sort of errors can you expect? Do you have any sense in that, just for the count or for the occupancy?
I think based on the data we use, the error sometimes, like, there's only one long vehicle per interval. And because the dual loop clock and the single loop clock may not agree. So you often see that in the single loop, you find a long vehicle in the interval n, but it shows up in the interval n+1. So if you compare directly these two intervals, the error is 100%, right? Because it's only one vehicle. But actually, it's just because of the time difference. So if you sum up all the measurements per day and look at the error, it's actually not bad. It's less than 8%. Is that, yes?
Did you say the loop detectors are located only in the middle lane, or are they located?
No, it's located at all the lanes. Like you have 5 lanes, and then you have 5 single loops, one for each lane.
So, does any of the data ever show the carpool lane, how effective that is or
Yes.
isn't? Because
Yes.
from my experiences up there, that lane always seems to be pretty crowded when I'm driving.
The carpool lane very crowded?
Mm-hmm.
Oh,
Yeah.
That's very different experience.
But I mean, maybe it's because it's my experiences. They're limited. I don't
Okay,
commute
I
on
think
a
you
daily
can,
basis.
like in our case, you can go to the Washington DOT's loop data website, and there the loop sensor code. You know which code corresponding to which sensor, because there will be a dictionary. You can just download the carpool lane. Like here in this system, if you choose this station, and you see there are a bunch of sensors. Those followed with the H is high occupancy lane. So you can download data like the loop code ES167D, MSH. That might be a carpool lane. You see there's 3, right? Because that's a dual loop station. You have 2 single loop detectors and also a dual loop. The T shows the speed track. The T stands for dual loop. S stands for a single loop, and the M stands for another single loop. If you know M, maybe just underscore.
You were talking about capacity earlier. Has there ever been discussion to get rid of the carpool lane and just open it up to all traffic? Would that help at all? Reduce,
I think in Washington, people also argued about that. And finally, I think maybe TRAC, the State Transportation Research Center at the University of Washington, showed some data and persuaded people to keep the carpool lane there. I think we should keep the carpool lane there, because in Seattle's case, the carpool lane is pretty empty. Like this morning, other lanes are congested, but we use the carpool lane because Ryan, Avery, and I, we carpooled to here today. So it guarantees that we can arrive the meeting at Washington DOT this morning and also here on time. Ryan, you want to add something?
Yeah, actually, I worked at Track last year with Mark Hallenbeck on some of that analysis, and they have actually done analyses on the carpool lanes, and one of the things that they look at is even though there may be fewer vehicles traveling in the carpool lanes and some certain locations, what they do is the proper measure to compare carpool lanes to other carpool lanes is not necessarily the number of vehicles, but rather the number of people in the vehicles. And so they've been able to show that on most stretches in the Seattle area, even though the volumes might be lower, the number of people carried is much higher. And in some areas, like you mentioned, the carpool lanes are actually relatively congested, which means that they can carry, in some cases, as much as 3 times the number of people that a regular general purpose lane carries. So they're definitely effective.
Good. So this is another system we just developed, and this is for monitoring a station, a single loop station, using the event data. Event data is a very detailed loop measurement. So we can measure vehicle speed and also classify vehicles into more categories. So here I'm demonstrating this system using the data we collected from I-5. It's true data, and we developed this program and selecting the algorithm. We choose 3 buckets here because we want to look at 3 vehicle measurements simultaneously. We suppose there any 3 vehicles collected here are not wrong vehicles. That means any 3 vehicles, there is at least 1 vehicle that's a short vehicle. So that's assumption, but you can change that from maybe you change the assumption to 5 up to 15. So according to the condition where you want to apply this algorithm or this system. So any other questions? Yes.
I have a question similar to a question which has already been asked. If you have a highway with 4 or 5 lanes of traffic in each direction, and you said that you have single loop detectors in every lane,
yes.
Couldn't you take one, or have you thought of taking one of the middle lanes in each direction and making a double loop detector with the assumption that the middle lanes being neither high occupancy lanes nor the lanes that people merge onto the highway in have similar traffic flow, and then compare the double loop lane with the single loop lane next to it?
I think that's a very good idea. Maybe Washington DOT or Oregon DOT want to do that. But the reality now is they put either single loops here or dual loops at this station. Probably if you want to handle the dual loop detectors, maybe the hardware or the controllers can have the capability. Once the capability is there, maybe they tend to place all the lanes with dual loop detectors. Because if you look at the traffic, the detailed data for each lane, actually the composition of vehicles are very different from lane to lane. Like for HOV, definitely it's just buses or cars. But the leftmost lane that's just next to HOV probably all smaller vehicles. And the rightmost one maybe lots of cars, lots of trucks. But if near the exit, and maybe the trucks switch to the second right lane. So you can put that dual loop detector at one of the lanes and help to collect some information. At least the speed should be close. I think that's a clever way to do it.
Well, I was just thinking of that as a way to test your algorithm.
the algorithm actually are all tested at the place with dual loop detector. Because if you have the dual loop detector, you take one of the single loop as the input loop detector and use the dual loop measures to be tested. Because I showed the curves, it's all compared with the ground truth data. So it's all already tested by this way, so we do not need that if it's only for testing the algorithm.
Before we thank our speaker, I'd just like to remind you that next week, Alan Lato and Mark Roden, they're both graduates of the MERP program here at PSU, will be speaking about looking to TriMet's future corridor planning and capacity analyses. And I know they're going to be talking about some of the VSIM micro-simulations they've done for the transit mall extension. So hope to see you next week in Neuberger Hall 454. And let's thank Professor Wang for his great presentation.
Thank you. Thank you. So if you have any questions after the seminar, feel free to send me email, or when you visit UW, you're welcome to take a look to what we are doing there.
Very good presentation.
Thank you.
Very informative. Is there a way